Okay, hello guys, can you hear me?
Yes.
Well, that's good. Okay, so this has been quite annoying. So sorry about that. As I explained to you guys, I had problems with my internet connection, so I had to relocate to a different place, and it took some time. But here we are. So let me just download the. Okay, so just let me download the slides in PowerPoint format and we can get it started. I know that we're starting with a 20-minute delay, so I'll try to ramp it up. And unfortunately, that probably means that we're going to skip our break that we typically have, halfway. But we'll see. We'll see how this goes. Okay, so let me come to screen sharing. And let's start talking about ultrasound. So can you see my screen, by the way?
Yes, teacher.
Yes.
Okay, that's good. Let me see. So let's do this. So let's start talking about ultrasound imaging and okay, let me see if I can also grab this just to have it just in case. Okay, so today we're going to start with ultrasonic imaging, which is the first modality that we are going to study like before we get into things like X-ray imaging and magnetic resonance imaging. It's probably the simplest one to explain, from a certain point of view. It has other complications for sure also, but we'll figure it out afterwards. And the first thing that we need to talk about is the wave equation. That's probably, step number one in this whole thing. So, so let's see. Ultrasound, to give it a formal definition, is a mechanical wave with an oscillatory frequency in the range of beyond audible, which actually means for humans 20 kilohertz and above. 20 kilohertz, actually I want to say it's probably close to 18 or something like that. It's probably suitable for people like yourselves, probably younger than you are even. For people like myself, I'm pretty sure my audible range is way below 20 kilohertz. Okay, but that's, you have to have some type of standard, and that's one of the things. So actually, ultrasound works in the clinical practice in a similar way. It's very, very akin to radar imaging. Most of the techniques actually that we have in ultrasonic imaging inherit from radar imaging. The pulse echo principle, echographic imaging, which actually is very, very similar to distance ranging with radars, or, like synthetic aperture imaging or even array imaging. We owe that from the radar community. Doppler, which is another big thing in ultrasound. We also inherited that from the radar community. Okay, so a lot of things that we're going to see again have to do with this. Not everything that we are going to see, um, but let's see how that goes. The wave equation is our first step, as I mentioned in this, because we have to understand how ultrasound waves are generated. And the typical starting point that
Teacher,
we have.
I'm sorry
Yes.
to interrupt you.
Yes.
I can see you're talking about the wave equation, yet the PowerPoint presentation is still on the main page.
Is it?
Yeah, I think you're sharing
Probably
just
you.
the presentation instead of the whole screen.
Yes. If you don't share the whole screen, then it doesn't move.
Seriously?
Yeah.
That's weird. That's weird and super annoying. Maybe it's because I'm in a different computer with different software, because I usually only
I could.
share the application that I need to share. That's super annoying. Let me see. Let me see. Right. So what you guys are basically saying is that if I do something like this, let me see. That's super annoying. Let me see. So what you're saying is that if I do this again and I keep switching, like you don't see the content changing?
Yes.
So it's not changing at all right now. Okay.
No.
That's
You could just project it from the software itself.
No, sure. I mean, I can share the whole screen. That's okay. It was just curious to me, I suppose. Okay, anyway, so I'm just sharing the whole screen, and right now you can actually see it changing.
Yeah.
Yes.
Yeah.
Yes, teacher.
Yeah.
Yes.
That's so annoying. Well, I love my computer more than ever, I suppose. So anyway, when we talk about the wave equation, and thanks for letting me know, guys, when we talk about the wave equation, we basically have three variables that are going to be related to generate an acoustic wave. And these three variables are the pressure, which is the force per unit of area, the density, which is the mass per unit of volume, and the particle displacement, which is the distance and the part that the particles are moved by an external force. So basically, there's that, right? I mean, we have three variables, and these three variables are related by three equations, right? That we need to integrate together in order to have a solution. So the three variables, again, related via three equations are shown in here. P, or capital P, is the acoustic pressure. Rho is the density, is the mass density. And what we have in here is the first of these three equations, which is the equation of state. The equation of state basically relates the changes in density and pressure. Okay, so I don't know if you guys take courses in thermodynamics, but does anybody remember that first equation in the slide? P divided by P naught, that would be the pressure divided by the ambient pressure, is equal to rho, which is the density, divided by rho naught, which is the equilibrium, or the equilibrium density, to the power of gamma, which is the specific heat ratio. Do you guys remember what that equation corresponds to?
Not really.
Okay, have you taken courses in thermodynamics, or had any lectures in thermodynamics? Have you heard about what an isothermal process is, or an isobaric process is? Things like those. Have you taken courses into that?
Yes, teacher.
Pretty sure you have, right?
Yes.
Okay, so you know about thermodynamic processes. Have you ever heard about an adiabatic thermodynamic process?
Yes, teacher.
What's an adiabatic process?
It's a process where the energy doesn't leave the system. No heat transfer, as Emilio says.
Correct. It's a process where you don't have any heat transfer, right? You don't have any net heat flow coming in or going out of the system, right? That's basically what it is. Okay. So with that set in mind, right? Again, do you recognize that equation over there as being the equation that governs the first equation, as being the equation that governs the behavior of an adiabatic process? Hopefully you do. So you, for example, if I were to tell you for an isothermal process, do you remember what was the equation that governs an isothermal process?
It's pressure multiplied with volume, I guess. I mean,
It would actually be very similar. It would actually be very similar to this one, right? With probably a small and big difference at the same time. Oh, so how do I activate this? No, I don't know, Control P or Shift P. No, I have no idea how to activate the pointer in here. Which is annoying. Okay, so the big difference probably would be that you would have, instead of a gamma, you will have a power of 1 in here, right?
Yes.
So that would actually be the difference. So again, when you have the adiabatic process, this is the expression, right? And it's just something, I mean, it's something that you have studied before. Hopefully you can, you know, go back to your materials and you can try to remember, right, every single detail about how an adiabatic process works. But in the end, even if you don't want to, it's an equation, right? And the basic thing to recognize in here is that it is a nonlinear equation. The fact that this is a nonlinear equation actually has very profound repercussions, okay, for acoustic wave propagation in general, that we're going to discuss in a little bit of detail afterwards today. But the point is that as good engineers, right, we want to always come to solutions of equations that we can actually analytically derive. And it is very, very challenging to come to a solution or a closed form solution of the wave equation if the equation of a state is not linear. The only way that it can be linear is if we were to be dealing with an isothermal process. But for better or worse, ultrasonic wave propagation is much better modeled as an adiabatic than an isothermal process, which leaves us with the issue of how do we convert the equation of state to an equation that is basically linear, that we can use for the purposes of deriving the wave equation. And the way that we do it is with Taylor series expansions. Do you guys remember how a Taylor series expansion works, or can somebody briefly describe what a Taylor series expansion is? Do you guys remember your Taylor series expansions?
It is. Yeah, it's a linearization. For the first
Actually,
component,
no,
for the
right?
first
I mean,
one.
not really. A Taylor series expansion does not, like per se, does not linearize a
Yeah,
function, right?
just
What does it
the
do?
first term. It actually compares a polynomial
Correct,
function with the
correct,
original function at a certain given point,
correct.
so
It
we can better approximate
expresses
the
any
behavior.
function as a polynomial around an expansion point, right? You expand a function as a series of monomials, and that expansion is valid within a neighborhood around the point that you use for the expansion, right? For example, one of the things that you know, and that's a tool that you very commonly use in engineering. For example, when you say that sine of x is approximately equal to x for values of x that are close to 0, right? That is basically a Taylor series expansion. You are linearizing the function sine of x with a first order polynomial around an expansion point, which is the point x equal to 0. And actually that approximation is a very, very, very good one around the value of x equal to 0. And it's probably a very bad one if you know, move away from that point. So those are the things that you have to remember. Like in general, right? If you go to any function and you analyze it locally, it may look like a polynomial. If you're like zooming really, really closely, probably for any function, right? You can approximate it even as a linear function for some vicinity around an expansion point. How big the vicinity is, it depends on the point that you're using for your expansion, okay? So in this case, what we do is we use Taylor series expansions to linearize the pressure around an equilibrium point, which is the equilibrium density rho naught, right? Because you can actually see that basically you can say that the pressure is equal to the ambient pressure multiplied by density divided by the equilibrium density to the gamma power, or the power of gamma. And that you can use Taylor series expansions, you can linearize it. And basically your Taylor series expansions would tell you that any function can be expanded as a summation from n equals 0 to infinity of x minus x naught being the expansion point, to the nth power multiplied by the nth derivative of the function with respect to the argument variable to the nth power divided by factorial of n, right? That's the formula for the Taylor series expansion. Well, you can do that for the first order one, right? And if you do, you only have one term, which is, in this case, it would be rho minus rho naught, right? Multiplied by the derivative of p with respect to rho, evaluated at rho equals to rho naught, which you can very easily do, actually, you know, like mathematically speaking. Then multiplied by 1 over the factorial of 1, right? Because this is only a first order term, which is 1. That is a very, very trivial expansion, actually. But the bottom line is that you can express P minus, you know, P naught is equal to, again, rho minus rho naught times some constant. And again, you know that that constant is going to be equal to the derivative of P with respect to rho evaluated at rho naught. That's what that constant is. For the sakes of, you know, knowing what the answer to this equation is and anticipating that, that constant we are going to call C to the square. So we're going to say that it is a strictly positive scalar value. And that value, again, C, that variable, is going to be equal to the sound speed in the medium. Okay, so that constant in the Taylor series expansion for us would be the sound speed to the square. Okay, so you can see that there is yet another term in here in this set of equalities that says that rho minus rho naught divided by rho naught multiplied by rho naught times c squared, right? So basically we're multiplying and dividing by rho naught. And that is giving us S times rho naught times C. S is a term that we call condensation, which again is the fractional change in density. It's density minus the equilibrium density divided by the equilibrium density, right? So it tells you how much the density is changing in percentage, right? Due to the acoustic wave propagating into the medium. The value of condensation for this approximation to be valid has to be very, very, very low. That is, we have to be in a close vicinity to equilibrium density for this to hold. You can actually work your way out of the wave equation with extremely large values of the condensation, but you would have to be mindful that if you do, your mathematical treatment is probably wrong, because you would be so far away from the equilibrium point that your linearization is probably no longer valid. Regardless, the condensation is a variable that's very commonly used in the description of the wave equation as this like adjunct variable that takes the place of the density itself. When we go to the second equation, we have the continuity equation, which is relating the changes in particle displacement and mass density. And this is basically the law of conservation of mass, which is basically telling us that the condensation, that is the fractional change in mass density, is equal to minus the derivative with respect to x, the spatial variable. We're assuming a one-dimensional space derivation for this. We're going to generalize it to 3 dimensions later on, okay? But for simplicity, we're dealing with a 2-dimensional space. So it would be minus the derivative with respect to x of the particle displacement. So can somebody explain to me the physical meaning of this equation?
Can I?
Go for it.
Okay, so this means that as the velocity of the particle changes around equilibrium point in a position of the wave, the density will vary over time.
Correct. Why? Why would
in other
that?
words, yeah, in other words, it means that to preserve the same amount of particles in a given place, the particles have to live at a certain. No, sorry, I'm saying other things. It means that as the particles move, the density will change locally. It's just that, I think.
Right. Although I like the way that your explanation was actually moving forward as the particles start to move, like in order to conserve or to preserve the same number of particles, in every point in space, all of them would have to keep moving at the same velocity, right? That's what it is. Imagine,
Teacher,
for example,
one question.
yes,
Does this apply
yes.
to gases?
It applies to fluids in general, gases
Okay.
and liquids. That's a very, very valid question. I don't go over the description of acoustic waves in solid media for the context of this course, which would be, something probably interesting for studying things like elastographic imaging, for example, simply because, right? That would be too much information. It overcomplicates things. But you're absolutely right. These equations are, technically speaking, valid fluid media, which includes liquids and gases. Thank you for the question. So imagine, right, and Like maybe this is something that that you can imagine, like if you go to non-creepy things like, I don't know, Black Friday in the United States. Well, actually Black Friday, like probably 20 years ago, right? When people actually went to stores rather than purchasing online. So maybe you have a lot of people, that are like crazy excited to get into a shopping mall, right? And they come from the parking lot, and they have a lot of space to just keep running, they go like smashing through the doors. But if the doors are closed, right? I mean, they can be like running at full speed, trying to make it to the shopping mall, like the inside of the shopping mall. But if the doors are closed, they cannot go beyond the doors. So what's going to happen is that you're going to have a crowd that's going to start forming in front of the gates, right? Because people cannot come in. So you can actually have them running, together as a group in the parking lot, right? And you can roughly see, well, I don't know, it's going to sound very nerdy, right? But maybe, I don't know, I have this many people per meter square, right, of surface on the floor. But certainly when you make it to the gates, because the gates are closed and people cannot keep running at the same speed, they have to slow down and they have to stop, right? Then what happens is that all of a sudden you have a lot of people crashing, through the door to make it into a shopping mall. You have a crowd. So the density of people per meter square would be higher, much higher, right? Or imagine again, you're in the highway and you have the cars, and the cars are, running at relatively the same speed. And then all of a sudden you're making it into the city and you run into the first stoplight, or you go through a toll booth, right? And you have to pay the toll. So the cars have to actually slow down because you have to stop and pay the toll, right? What's going to happen is that in the toll booth, right, if you could actually look at how many cars you have, likely you have a conglomeration of cars. Like the number of cars, again, per surface on the highway would be higher than if you go several miles behind and you just go through the lanes of the highway and the cars are running wild and free, right? That's something that we see. It's something that just makes common sense. If things can keep moving at the same speed and nothing stops them from doing so, then you have a certain number of particles leaving a differential of volume, and you have the same number of particles coming in. So the density doesn't change. The number of particles that you have in a volume never changes, because the same number that comes out comes in. But if by some reason, the velocity of the particles start to change, then that's not going to be the case anymore. You're going to have a conglomeration. Okay, so that's what this expression is telling you. And in general, people that know me will know that when I teach something, I like to talk about the physical meaning of the equations as much as I like to talk about the equations themselves. Because I think one thing needs the other. And I also think that's the way that engineering happens. I don't know a good engineer, for example, when you work on your undergraduate thesis, if you ever do one, it's great if you get to read and read and read about, the things that you need to know to work on your thesis, but you should probably also work on your thesis at the same time. Engineers learn via experimentation and informed reading. Both things are necessary, okay? So in here, in this equation, like the actual continuity equation is the first one. The one in the second row in this slide, it's actually the same one, but you're taking the derivative with respect of time. Because this is a function that's assumed to be like particle velocity, which is the squiggly symbol, right? And S is the condensation that we defined in the previous slide. So the derivatives with respect of time and space are interchangeable because these are continuous functions of time and space. So you can swap the order of the derivatives, and you have the derivative with respect of time of the particle velocity, which we call sorry, the particle displacement, which we call the particle velocity. So that variable u is a particle velocity, and it's a very important variable to us actually. The particle velocity is going to be the equivalent, for example, for electrical engineers in here in the audience, or even, biomedical engineers that have taken courses in electrical circuit design. Then you know that in electricity, you have a potential, which is a differential in voltage, and you have a flow that is produced as a result. And the flow would be the electrical current. It's electrons moving, right? So in here, you will see something extremely similar. You will have a difference in potential, which is the pressure. And as a result, you produce a flow, but you don't produce a flow of electrons. You produce a flow of particles. And that flow of particles is characterized by the particle velocity, which is a component that's telling you at which speed those particles are moving. Okay. So we go to the next slide. And the third equation is the equation of motion, which is relating the changes in pressure and displacement. And this is actually Newton's second law in disguise. So can somebody explain this equation to me? This probably should be the easiest one of them all to explain.
It's I mean it is the equation of impulse. The pressure with the density, area and volume cancels each other, and you got the impulse equation.
Sorry, the impulse equation you said, I don't recall that expression. Can you elaborate a little bit more, please?
Yeah, the how do you say it? Quantity of movement? That's it.
So the equation of, well, the equation of motion, right? But I mean, actually, if you were to look at this equation, you know this equation, right? In which form do
Yes.
you know this equation?
Force is equal to mass multiplied by
Times.
acceleration.
Correct, right? Because mass is like density is mass per unit of volume. So showing the density is an elaborated way of showing the mass. The differential of a velocity with respect of time is an acceleration, right? And then you have forces, but the pressure itself is force per unit of area, right? The differential with respect to x is basically giving you, the difference is actually the net force, right? Net force is equal to mass times acceleration. This would be giving you the net force in itself because it's the change, in one differential element. To the left and the right, you have pressure in one location, pressure in one location plus differential of x, right? So you have a net force per unit of length, per unit of area. And that will be per unit of volume, which cancels out with the volume of the density on the left-hand side of the equation. And again, you have mass times acceleration equals to delta of forces. It's the same equation that you know from before in a slightly more elaborated fashion. Okay. So again, every time that you look at equations, like do yourself that favor, right? Don't just look at equations and think, oh crap, this looks super gross because there's like a lot of symbols I don't understand, and move on. Try to understand them within the realms of reason. So we have three equations and we have three unknowns, and we can actually try to come up with a solution. And yes, exactly, Emilio, mass times acceleration equals force, which is what you typed in the chat, right? So we can try to combine these equations, and if we do, we can show that the acoustic pressure in a homogeneous medium is going to satisfy the equation that we have in here. Second derivative with respect to x to the square of the pressure is equal to 1 divided by the sound speed to the square times the second derivative with respect of time to the square of the pressure. This is a relatively simple second order differential equation that we are going to demonstrate what the solution is before the end of this lecture. Okay, but I'm pretty sure you have seen something like this in some of your courses in physics in your undergraduate education. And if you haven't, then, which I'm pretty sure you have, then we're going to discuss, how to relate this back to some of your training in physics. That's kind of the cool thing when you make it to, the courses in your final years in formal education, is that you can go back to all the things that you learned, for 4 or 5 years or so, and you can take pride in knowing that, there's a whole bunch of things that you learned and that you can use for something else. Before we do that though, and this is just as a formality, right? Because this is something that nevertheless you can just wonder, okay, great, but there is no medium that's one-dimensional, right? We don't live in a one-dimensional world. We live in a three-dimensional world. And even if you want to, think about this in terms of like imaging happens in 2D, right? And again, there is no two-dimensional world, but sometimes we make simplifications, and in imaging, the lowest we go is to 2 dimensions, which means that we're still in a multidimensional space. So when we do that, the equations are exactly the same, minus, some very subtle modifications. And those come in the way of the continuity equation and the equation of motion. The continuity equation, remember, relates the condensation with, in this incarnation, it would be the particle velocity. But when we reside in a multidimensional space, we know that the velocity is a vector, right? The condensation is not a vector, it's a scalar, because the condensation is simply telling us what is the changing fractional density. That's the only thing that it's saying, right? So we need to relate a scalar with a vector. And the way that you relate a scalar with a vector is via a nabla operator, which can be either a gradient or a divergence. You guys have read and studied gradients and divergences, right? Like in some of your general studies courses. I mean, I know I did, but do you guys remember what a divergence is and what a gradient is? Are any of you familiar with those concepts?
Yes.
Can you maybe briefly remind the rest of the group what a divergence is and what a gradient is?
Yes. Well, in this case, it's a divergence, and it means that I mean, it's basically deriving in each direction, partial derivative in each direction of the physical quantity that is velocity in this case. And the further meaning is that how it goes away from a given point in space.
So a divergence is basically an operator that transforms a vector into a scalar. That scalar being simply the combination of the derivatives or the sum of the derivatives of the function in each and every one of the spatial variables. So in this three-dimensional case, the divergence of u would be the derivative of the x component with respect to x plus the derivative of the y component with respect to y plus the derivative of the z component with respect to z, correct? That's what it is. I mean, the nabla vector, it's actually an operator, it's not a vector, right? And this operator has the first component being the derivative with respect to x, the second one is with respect to y, the other one is with respect to z. The inner product, right, which is the dot representation that you have in there, it means that what you're going to do is you're going to apply, well, this is an inner product, right? So the first component times the first component plus second component times the second component plus the third component times the third component, right? Vector to vector. And that's where the definition of the divergence comes. In the same way that in this case, the equation of motion relates the particle velocity, right, which is a vector, to the pressure, which is a scalar. The pressure field is a scalar field. So in this case, we need to convert the pressure to, or the derivative of the pressure to a vector field. And that we do with a gradient. So it's the same concept, but in this case, it's multiplying a vector with a scalar, right? Which basically what would do is you multiply each one of the components of the vector times the scalar. So in this case, you again have derivative with respect to x of pressure, the second component being derivative of y, the pressure with respect to y, and the third component would be the derivative of the pressure with respect to z, right? So it's the same idea, right? It's nothing groundbreaking, right? It's just the nomenclature that it follows, and you can actually very easily show this yourselves from first order principles, but you can take it for granted too, because that is the way that the expressions are related when you are dealing with multidimensional spaces. And you can actually do the same thing that we did before, you know, combine the three equations. And spoiler alert, that's going to be like for a scalar version of the wave equation, that's going to be in your first homework. So be mindful of that, just for fun, you know, it's not that tough. And you can actually show that in this case, it would be the Laplacian of the pressure is equal to 1 over c squared times second derivative with respect of time of the pressure field, right? With the Laplacian being the nabla to the square operator, and is defined as the second derivative with respect of x to the square of the pressure plus second derivative with respect of y to the square plus the second derivative with respect of c to the square. So, I mean, that again would follow, you know, from a direct manipulation of the vectorial equations, and you would, you know, still make it back to an equation that's very, very close. It is almost a trivial-like extension of the equation that we had before. Do we have any questions up to this point? Do you have any questions up to this point? Okay, fantastic. Then I overestimated the fact that I'm getting old and I need some water, you know, to drink and sip every once in a while. So just give me 5 minutes. I'm just going to get a glass of water. You can, you know, get up, stretch your legs and relax, and we can come back to resume the lecture. Okay, thank you guys. Thank you. See you in a little bit. Okay, guys, let's resume this so we don't run out of time more than we have already. Okay, and we are recording. Yes, we are recording. Okay, if not, that would be a disaster. Okay, so let's keep going with the wave equation. The wave equation, again, is something that in principle you should be able to solve, but it may be that it's more complicated than it would originally seem. But there is one thing that you can do in order to have a very manageable equation to solve, which is dealing with the case of harmonic waves. Harmonic waves are waves that in principle, you know, the pressure field depends on x and t. We are, you know, going back to the case where we have a simple one-dimensional space, because it just simplifies things notation-wise. So we have a pressure field of x and t, which we are going to assume that the temporal dependency is just given by an e to the j omega t. That is, it would be a complex sinusoidal of time at a single frequency omega. That's where the name comes from. It's a harmonic oscillation, right? Times p hat of x, where p hat of x is just, it's a function of x, right? So the pressure field changes across a space, but across time, it basically oscillates as a single frequency. Is this particular case a harmonic wave? Is it one that makes sense to us? Do you guys think that that would exist, in the real world to begin with? Or why is it that this particular case would make sense, or it would be, worthy of a study? What do you guys think?
I mean, as we were talking at the beginning of the class, like most of medical imaging comes from pulse, like pulse modalities. So it does make sense for harmonic waves to like be used in medical imaging.
You mean because of the ultrasound waves being pulses, and like oscillatory pulses and such?
Yeah.
Sure, I mean, potentially that can be a very valid reason. But even if they are pulses, right? I mean, they would still, like, in order for a model like, a complex sinusoidal to be valid for the temporal, variations, then you would think that it will have to be a super long pulse, right? And also, this is sort of assuming that in every, like, the whole dependency is equal to an E j omega t, right? Every single point in space has the same temporal dependency, which seems a little bit excessive and harsh, right? I mean, you would think that maybe that could be softened in a way. So for a lot of people, it's not very intuitive that this indeed can be realistic to begin with. I mean, for sure, I can write down the equation, right? I can always write down any equation that I want. It doesn't necessarily mean that it's intuitive, though. So what do you guys think? We have actually, talked about the justification for this being reasonable in one of our lectures from last week. Just to give you a spoiler on one hand, and to sort of guide you to the answer that I'm seeking for. But why would this be reasonable from a mathematical point of view? Yes, Breno.
I mean, these are harmonic waves satisfy the condition if we solve the differential equation above and use a Fourier transform method. So in the end, it serves to express the waves in the frequency domain too.
Well, actually, I'm going to take parts of what you were saying right now, and you're absolutely right. The reason why this expansion is actually meaningful is because if you seem to recall, right, from our lecture number 2, I think it was, we have a Fourier transform, right? So whenever you have Fourier transforms, imagine that, well, you don't have to imagine. In this case, we have a function of x and t, right? T being time. If you take the Fourier transform with respect of time, so it wouldn't be a two-dimensional Fourier transform, it would be a one-dimensional one, right? What does that mean? It means that, by the definition of what the Fourier transform was, and you remember that from our last lecture, right? It means that any function that is a function of time can be expressed as what? As an integral or a summation, right? If you do this computationally with a discrete number of frequencies, it would be an integral of some coefficient, right? Whatever the name would be, some coefficient times e to the j omega t. And if it's an integral, then it would be differential of t. And these coefficients, we know that, they can be derived using the synthesis version or the definition of the inverse Fourier transform, right? But regardless of that, we know that, any function of time can be expressed as a weighted combination of complex exponentials. That's what the Fourier theory tells us. And it's very, very powerful because it means that for this two-dimensional function of x and t, I can actually take the Fourier transform with respect of t, right? And it's going to give me a coefficient. Remember, I'm only doing this for t, right? So it's going to give me a coefficient, and those coefficients are going to be different in every point in space. But Fourier theory would tell me that in general, right, it would be a coefficient times the complex exponential. And that's what allows me to say, well, if there is some strange function of time that I want to model, that's okay. Because I just have to invoke the Fourier transform and argue that if I were to know what the coefficients, for synthesizing the function is via the inverse Fourier transform, then I could always synthesize, that response to the wave equation by properly weighting the responses for different frequencies of interest, right? And that's basically a rationale. And that's why we discussed, a week ago, that the strength of the Fourier transform is basically that, right? Is that idea that scientists refused to acknowledge when this was first published, that any function, even a discontinuous function, could be expressed as a linear combination of complex exponentials. Okay, so with this brief, not so brief, discussion of why this makes sense. So again, if anybody asks you again, why would harmonic waves make sense? You can simply say they make sense because on their own, they don't mean anything. There are no harmonic waves in the real world. But because of Fourier theory, I know that any function of time can be decomposed as a linear combination of complex exponentials of time. Any function. So if I know the solution of the wave equation considering a complex exponential, a general one, then by Fourier theory, I could potentially calculate a solution for any waveform that I want, that has any distribution, like arbitrary distribution in space that I want. Okay. So if we were to have this, right, if you look at the expression in here and you plug it into the wave equation, you get to the second one, which tells you that the Laplacian of p hat plus omega squared divided by c squared times p hat, where we actually define yet another variable. We like to define variables, right? We define the variable k. K is called the wave number, okay, which again is the ratio of omega, the angular frequency, divided by c, the sound speed, is equal to 0. And this expression is known as a Helmholtz equation. Has a name, right? And it's very well known in physics. Now, actually, you must have seen this in a physics course before. In which context have you looked at the Helmholtz equation in the past? Who wants to elaborate? Where have you seen the Helmholtz equation? Like used for what in the past?
I remember something similar in physics too.
Right. Exactly.
Yeah.
So it's still physics too.
For vibrations.
So who wants to complement that? It's not that I don't like people who participate, but Emilio and right, Emilio and Breno have been participating a lot. So actually two Emilios have been participating a lot. So does anybody else want to contribute? So Helmholtz equation, what did you use it to model in the past? Come on, guys, don't be shy. Own your courses. Anybody? You guys know we can be here all day, right? So I have a lot of patience. So like I'm curious if this is because you guys are shy or because you don't even remember what the Helmholtz equation looks like, which would worry me a little bit, not because of you guys, it would worry me because of just trying to scratch my head thinking if we're doing a good job, you know, teaching you the things that we're teaching you. So it's thinking about us professors, not you students.
It remembers me something related with magnetics. I think it's related with Maxwell's equations.
Right, that's true. If you have taken courses in electromagnetics, you've certainly seen this in the context of Maxwell's equations, right? And to some extent, you know, people in acoustics call the three equations that we saw before, right? The equation of state, the continuity equation, and the equation of motion. People call them the Maxwell's equations of acoustics because it's the same idea, right? In the case of electromagnetic waves, you have the E field and you have the H field, you know, or the B and the D, depends on, you know, how you want to solve it. And you have your charges and you have your equations and everything is a vector, right? Over there, everything is a vector. And it's a more complicated derivation in general than the one that we have looked so far, but it follows along the same lines. That's true. I think that somebody also typed something in the chat. Well, yeah, sure. Emilio said Maxwell's equations too, right? But Breno is okay and correct in saying something. Even before you saw that, right? Even before you saw Maxwell's equations, waves are waves is something that a lot of people would tell you in the physics community, right? So electromagnetic waves or, you know, acoustic waves are sort of, you know, the same basic principles occur. If you grab yourselves a nice book in electromagnetics, you know, for a cozy afternoon, sipping a hot cup of cocoa on your couch or something, you will see that, you know, topics like resonators, you know, like transmission and reflection of waves, like so on and so forth. I mean, the description is almost the same, you know, potentials, everything's roughly the same. Again, it's typically more convoluted, you know, in EM because of the vectorial nature of the fields and waves. But you have probably seen this in a simple mass spring system, right? The Helmholtz equation would be the one that would correspond to a super, uber, mega simple mass spring system. And that is something that we're going to talk about in a little bit, because the solution to the Helmholtz equation in one dimension, I think I have one message in the chat too. Right, point source vibrations too, correct. So we'll get back to that, okay? So for example, in plane waves, right, which is, this is the name that the solutions have, we have a second order differential equation. So even without me, you know, coming to this slide, if I were to ask you if you have a second order differential equation, how many solutions do you have? If it's a second order ordinary differential equation, how many solutions do you have? You can do it, guys. How many solutions?
Two?
Yep, there you go. You have two, right? And that is something that you also probably learned a lot. I want to say probably in high school, but you know, for sure in general studies. Yes, you have two solutions. And the solutions are the ones that are shown in this slide. Pressure as a function of x and t is equal to some amplitude, which, some amplitude, God knows, is just a scalar number, multiplying the exponential of j omega t plus or minus kx, plus or minus, right? Those are the two options. Those are the two solutions, which if we factor out the omega, right, what we have is amplitude times e to the j omega t plus minus x divided by c. So it's time plus minus distance divided by speed. The first solution represents a wave that travels to the left. The first solution being the one with the plus kx. The second solution, the one with the minus, represents a wave that travels to the right. And just for your own personal knowledge, we have yet another variable, right? Which is a wavelength that we're defining here as, 2 pi divided by k. Equivalently, that would be c divided by f. Or equivalently would be c multiplied by t, where t is the period of the signal, right? We have an oscillatory signal at a given frequency f or an angular frequency omega, right? So that has a period, and we have a period that we call capital T. And you can see from this expression over here that if lambda is equal to c times capital T, right? Capital T being in units of time, lambda being in units of space, and of course, c is given in units of space divided by time, right? Or distance divided by time. Then we know that the wavelength is basically the distance equivalent of the period, right? What you're having here is an oscillation that occurs both in time and in space. Meaning, if you were to plot the wave for a fixed moment of time, that would be in different x locations, you would see an oscillation. If you plot it at a fixed x location, right, for many moments of time, you would also see an oscillation. That's why it is. Okay, and these oscillations manifest themselves again, periodically in time with a period of t, and periodically in space with a period of lambda. The period being in units of time for t and in units of space for x, or lambda in this case. Questions up to this point?
It is a doubt I got the last time after reviewing. Sure. That the equation for the plane wave assumes a medium that has already been perturbated.
Okay.
I mean, if we plot it, I would see an infinite oscillation in a plane.
An infinite oscillation, if we plot it as a function of which variable, sorry?
Of position, for example.
Okay. So for example, I fix a moment of time and I look at space.
Yeah.
Okay, sure.
So I would see like a wave of a sea of waves, for example.
You would actually see an oscillation that goes from minus infinity in x all the way up to plus infinity in x. Correct. Correct.
So my question here is that when we,
how on earth that happens?
I mean, yeah, I mean, if because the last equation of the Helmholtz equation is a point source, right?
No, Helmholtz equation is not a point source per se. It just assumes that Helmholtz equation arises from analyzing the wave equation right? Assuming that the behavior in time is a harmonic function.
Oh, okay. So why did we use it for point sources? I remember it.
I mean, sure. I mean, there are, I mean, this is, okay, so let me see, blah, blah. We also do this for, or it also deals with point sources. But we're going to talk about that in a little bit. Right now, like that happens when you analyze this in spherical coordinates. Right now, we're analyzing this in Cartesian coordinates, and the solutions end up being plane waves.
Yes.
Mm-hmm.
Maybe I just keep listening and my doubts
Sure,
could be
no
clarified
problem.
then. Yeah.
Yeah, of course, you can bring it up again. In ultrasound, we only use plane waves. I heard about transverse waves, and I would like to know the difference. Well, actually, that's probably that's probably a little bit confusing terminology. You're probably thinking about like longitudinal waves and transverse waves to begin with, right? So I think one of you was referring back to the Physics 2 course, I think, where you studied things like a spring and a string, right? One
Yeah.
with a P and one with a T. And the string is a model for what type of waves, longitudinal or transverse?
Transverse.
No, longitudinal actually, almost.
Yes.
The string, right, is the one that is the model for the transverse waves.
Okay.
Longitudinal waves mean that the oscillation is in the same direction of energy propagation.
Okay, I remember.
Right? So for example, you have the mass and the spring, right? And you grab it, and what happens is that the spring starts moving left and right, left and right, left and right, right? With the energy propagating in the X direction.
Yes.
When you have the string, right, which is basically that, right? Like the string of a guitar, for example, and you pluck it, right? What happens is that the oscillations occur going up and down, up and down, up and down. But they actually, the energy propagates away from the point where you plucked the string to the left and right. So the direction of energy propagation is transverse to the direction of the oscillation, right? So when we have waves propagating into a medium, we can have two types of waves. We can have, again, this one is a longitudinal wave, or we can have a shear wave. And shear waves are modeled by, transfer. These are types of transverse waves, right? They have a transverse motion. And those actually only occur in solids. They don't occur in fluids. In order for the medium to support that type of behavior, there has to be, there has to be, well, to begin with, a shear-like behavior in the medium, right? Meaning that if you produce an excitation in one direction, it's capable of producing deformations in other directions too. That doesn't happen, like imagine in air, right? I mean, you just, like, I know you push up with your hands, like probably very hard, and you're not like generating, I mean, you're moving the particles up, right? Of course, after that, there's going to be some turbulence and still in that, but you're not pushing the particles to the front. That happens when there is some sort of a lattice structure that holds the particles together. And that happens in solid media, not in fluid media. That is the whole basis for elastographic imaging, for example, right? But again, if I were to go back to the basics, I would tell you that the difference is basically that is the string versus the spring model for motion in, you know, like when we deal with mechanics. So hopefully that addresses your question. Do we also only use plane waves? We actually don't use plane waves all that much in ultrasonic imaging. And that's probably the point where I was saying that there maybe there's a terminology thing in here. A plane wave is a type of solution, you know, to like in this context that we're studying it, it would be a solution to the Helmholtz equation that we're deriving for fluid type media. All right, so if you do this for shear waves, it would actually be exactly the same solution. It's just that you derive it via potentials. And again, that's a little bit more complicated, but not really like a lot. It would just take a lot of time, you know, we will have to have a complete course in ultrasound for that to happen. But a plane wave, like when we deal with ultrasound and when we deal with propagation in, you know, in fluid type media, we don't produce plane waves either. A plane wave, because going back to Brenda's question, right? Like he was saying something that's very fundamental. Like if I were to, for example, fix a moment of time equal to 0 even, right? Like looking at the solution that we're showing in here, a plane wave, implies that I have oscillations going from minus infinity to plus infinity in space. And that's a big WTF moment, right? Because you would assume that, well, I turn on the system at time equal to 0, right? So how on earth did the wave actually make it to minus infinity and plus infinity in space? Because it's meant to take some time for that to happen, right? That's probably where Brandon's question was going to, because it really does feel, you know, bizarre. Like how does the pressure field exist in the whole space if the wave has not traveled there yet? Does anybody have an answer to Breno about that? And I'm guessing, you know, Emilio maybe would, like one of the Emilios, actually, I think it was, you know, the one that was talking about the reason why we use, you know, harmonic fields to begin with. Maybe probably, you know, from the point of view of the discussion we had, maybe you can elaborate on that. And if no, no pressure, no BE, you know, like, I don't know if anybody would have something to say about this. Sure, no problem. So the reason is because, remember what I said, harmonic fields, like analyzing the response to a harmonic field or a harmonic oscillation. Harmonic oscillations are complex exponentials that happen, you know, from minus to plus infinity in time, right? So because it goes from minus to plus infinity in time, it really means that, you know, the system didn't start oscillating at time equal to 0 or at any other time. You know, like it's like going to the Bible and saying, you know, the first day God created. No, sorry, even before that, there was an oscillation, you know, like it's like whatever. So the oscillation actually, you know, from a formal point of view, because it started at time equals to minus infinity, it's been there forever, right? And that's the reason why, Breno, you know, when you look at the solution and you think, what happens if I fix this at the moment of time? How on earth did the acoustic wave already made it, you know, to x equals plus infinity? It's simply because it was turned on since time equals minus infinity, you know? So it already had infinity time to travel to infinity space. Does that make sense?
From the formula, yes.
Right. And as I said, right, and that's what Emilio was saying. So maybe because, you know, when we have ultrasonic waves, you know, they look like sinusoidal oscillations? Yes, and my answer was yes and no, because regardless of that, they have a duration, right? Because they have a duration, it simply cannot be, right, that they would be corresponding one-to-one to a purely harmonic oscillation. They would have a bandwidth. So if you look at just one of the components, just like, for example, saying, okay, any function of time can be composed by a series of harmonic oscillations in time. So a finite signal is composed of a lot of infinite signals, right? If you look at one of those sinusoidals oscillating in time, I mean, of course it's infinite, right? I mean, it goes from minus to plus infinity. And you don't have a way of saying like, this only occurs, you know, between time equals, you know, 0 and 1. You lose it because you're looking at an infinite time response. In order to really get the signal you want, you have to combine many of those things. And when you combine all those sinusoidals, you get a signal that is finite in time domain, correct? So it's the same idea, right? When you combine the responses to those oscillations, infinite oscillations in time, which give you infinite oscillations in space. But as you combine them, the infinite oscillations in space will produce you something that has a finite span in space. You just won't see it if you look at one harmonic. The reason being, in the real world, there is not one harmonic. Even if it's a long signal, it has a bandwidth, meaning that in order to really understand the response, you will have to combine, you know, solutions at many frequencies. And when you combine them, that's when the magic happens. Okay, that's why, for example, in the previous lecture, we had that rectangular function, you know, we were showing graphically that you can compose it by combining infinite many oscillations, right? Which is something that intuitively at first, for people who are not used to Fourier analysis, it may look counterintuitive. But as you keep adding more and more, if you just look at one oscillation, it's just one oscillation that looks nothing like a rectangle. But as you keep adding more and more, things start to cancel out and you start to see a shape. Okay? Awesome.
Yes.
And that's what a plane wave looks like, right? That's basically what it is. I mean, it's a signal that is changing in a space and it's changing in time. And in both instances, it changes like a sinusoidal, right? And you can see that, that's where the name comes from. The name plane wave means, or it comes from the fact that, you know, every point that shares the same amplitude happens in a plane, right? So you can see this, you know, it's like the plane, like time is passing by, and as time is passing by, you know, you have X and you have Y, and this thing is propagating in, I don't know, let's call it X, right? You can call it whatever direction you want. It's just propagating in that direction, and it's doing its plane wave thingy, right? Same amplitude always, like the maximum, the peak amplitude of the wave is the same, and it just keeps marching on and on in its, you know, travel direction. Okay, graphically, that's what it is. It's what Bren is saying, right? I mean, it just keeps going on. A couple of definitions in here, also talking about another variable that, I mean, believe it or not, we're basically laying out the foundations, you know, talking about all the equations that eventually we're going to need to boil it down to two things that we are going to particularly care. One of them is the definition of reflection and transmission, which we're going to see before the end of the lecture, hopefully, but God knows. The other one would be beamforming, which we're going to spend quite some time talking about. Okay, and we're going to define what beamforming is. And for that, again, we need to lay down the foundations of these kind of things. So there is a concept of impedance. And as I said before, right, the analogy with an electric field is that you have voltage and current for electricity, you have pressure and particle velocity for mechanical waves. And just like you have an impedance for these electric fields that would be voltage divided by current, you have an impedance for mechanical waves, which is pressure divided by particle velocity. Okay, just like in the case of electric circuits, right? Where you have transmission lines, which I don't know if you got to study proper. I'm going to say maybe you haven't studied transmission lines, which is the case where you have a distributed voltage field, right? And therefore you have a distributed current too. And these are functions, right? Unlike the circuits that you have probably seen in simple circuit analysis, where you basically have a value of a voltage in a wire, and you see a drop in voltage as you go across a resistor, things like those. When you have transmission lines, you have a progressively changing value of the impedance because you have a progressively changing function, right, of voltage and current, and you have reflections of voltages, currents, and things and stuff. That's probably more complex than what you have studied. And to be quite honest, I think even as an undergrad in electrical engineering, I wasn't taught about transmission lines, which is kind of bizarre because I think every electrical engineer should know about that. But that's the same idea in here. And just like in the case of electrical circuits, there's also the idea of the characteristic acoustic impedance, which would be, equivalent to saying I have a resistor, which has a value of impedance of resistance, actually, of, I don't know, like 100 ohms, right? Something like that. So this would be a value that is just given by the properties of the medium. And in particular, the characteristic impedance of a medium is equal to rho naught, which is the equilibrium density, multiplied by c, which is the speed of sound. Okay, so there's that difference in there. The specific impedance depends on the wave that you're dealing with. The characteristic impedance only depends on the properties of the medium. Any questions up to this point?
Yeah, teacher.
Okay, let's keep marching then. Equivalently, again, just like what you have with electric fields, you have intensities. And the intensity is defined, again, just like in the electric case, is the expected value of the real component of the pressure multiplied by the real component of the particle velocity. So you have a periodic wave that basically means that you have 1 over t, which is the period of the signal, multiplied by the integral from 0 to t, the period again, of the real part of the pressure, multiplied by the real part of the particle velocity, integrated with respect of time. The acoustic intensity, it's a value, basically, right? You can also have the instantaneous acoustic density. These are the expressions for the average one, right? So instantaneous one would be just the real part of the pressure times the real part of the particle velocity. And you can actually very easily, for a plane wave, derive what the expression for the average sound intensity is. The acoustic intensity is also expressed in decibel scale, and typically it is expressed in decibel scale because sound and ultrasound, changes values across several orders of magnitude many times. Okay, so it's very convenient to express it in the scale that's shown here, which is a decibel scale, which means 10 times log 10 of the ratio of the intensities, or 20 times logarithm base 10 of the ratio of pressures. Even though both things look kind of different, the reason for them actually being completely equivalent is that you can demonstrate, for a periodic wave, or for a plane wave in particular, right? You can demonstrate that the intensity is proportional to the pressure to the square. So if the intensity is proportional to pressure square, that means that 10 times logarithm of intensity is equal to 20 times logarithm of pressure. It's the same thing, right? Because one is proportional to the other one to the square. So that factor of square comes out of the argument of the logarithm and multiplies that 10 in front. And that's where you get the 20. So for example, going back to the plane waves, we can try to calculate the particle displacement, the particle velocity, the specific acoustic impedance, and the average intensity. And we actually come to this, right? And we can very easily argue that with all the equations that you had, right? So if we use the equation of state and continuity, for example, we can easily derive that the particle displacement is equal to minus j divided by rho naught k c square times e to the j omega t minus kx. That would be for a plane wave traveling to the right. The particle velocity would be obtained by taking the derivative with respect of time of the, well, actually there's a mistake in here of the particle displacement, not velocity, right? And if we do that, then you have the expression of u, which is 1 divided by rho naught c times e to the j omega t minus kx. So just by looking at this expression, what would the specific acoustic impedance be equal to? Remember that the specific acoustic impedance would be P divided by U. So what would that be equal to?
Just P divided by U.
P divided by U, correct? So if
Yeah, that's
if I do that, then what would be the result?
P over rho naught multiplied by C multiplied by all of it multiplied by exponential of minus J.
P is actually equal to e to the j omega t minus kx, right? So P being e to the j omega t minus kx, and I divide by U, which would be e to the j omega t minus kx divided by rho naught c. That is equal to rho naught c.
But what I got lost. P.
So
Oh,
we
okay.
already
P is
said that
the yeah. Okay, the
P is the
Helmholtz, right?
pressure, right?
Yes, yes.
Correct. So P is equal to e to the j omega t minus kx.
Yes.
We divide by that expression of U over there, and what we end up with P divided by U is equal to rho naught c.
Mm-hmm.
So that means that for a plane wave, what we have is that the specific acoustic impedance is equal to the characteristic acoustic impedance. There is one caveat though, okay? There is one tiny little detail. You can actually show very easily probably that if the plane wave is moving to the left, that is, the pressure would be e to the j omega t plus kx. The particle velocity turns out to be minus 1 over rho naught c e to the j omega t plus kx in this case. So when you calculate what the acoustic impedance is, the ratio of P divided by U is not rho naught times C, it's minus rho naught times C. So there is a factor of -1, in there, in the specific acoustic impedance when you are dealing with a plane wave traveling to the left rather than to the right. Okay, just be mindful of that because that's going to be important eventually, in some other portions of this theoretical discussion of acoustic waves. There's another couple of details that I probably want to go over with you before we wrap it up, because we're already over time, and I know for all I know you have other courses and stuff. So there's a couple of concepts in here. The first one is attenuation. We have been talking about a wave, that matches this like concept of a system of masses and springs, right? But there are no dampers. There is not a lossy term in the system. And if you remember, right, in your physics courses, you studied a system of a mass and a spring and a damper. And what the damper did was it reduced the amplitude of the oscillation because it opposed the velocity, right? Just like the spring opposes the displacement, here by via Hooke's law, you have a system in which the damper opposes the velocity. The faster you move, the stronger the force that opposes it, right? So it basically dissipates the energy over time. So the same thing happens, with the pressure fields, and you can actually introduce a concept of a complex wave number, which results in a general solution that also takes into account for losses in the system. And the meaningful or physically meaningful solutions consider that, the attenuation or the loss of energy is going to occur as an exponential function. So the deeper you propagate into the medium, the higher the loss of energy is, and that loss of energy follows an exponential law. That attenuation coefficient alpha has units of Nepers per meter. Nepers is adimensional. It's like saying radians. So Nepers per meter is like saying meters to the -1. Now in ultrasound, we typically express the attenuation coefficient not in Nepers per meter, but in decibels per centimeter. Moreover, we typically refer to the attenuation coefficient slope. An attenuation coefficient slope is nothing more than the change of the attenuation coefficient as a function of frequency, assuming a linear dependence. For example, for soft tissues, the typical value that is assumed that the attenuation coefficient slope has would be 0.5 decibels per centimeter per megahertz. Okay, so what does that mean? That means that, for example, if we have something at the depth of 1 centimeter, right? It's round trip because we have to go, from the transducer 1 centimeter deep, and then from 1 centimeter deep back to the transducer. That's 2 centimeters overall distance that the ultrasound wave has to travel. So it would be, 0.5 times 2, that would be 1 decibel per megahertz, which means that at 1 megahertz, the ultrasonic wave is going to be attenuated by 1 decibel, which is nothing. But at 10 megahertz, the signal would be attenuated by 10 decibels, which is an order of magnitude. In general, that's what happens with ultrasonic waves. The higher you go in frequency, the higher the losses due to attenuation when you propagate deeper into the tissue. And that's going to have a profound implication on the way that ultrasonic imaging works, in the sense that you are going to have a trade-off between how high you want to go in frequency and how deep you can penetrate into the tissue. Higher frequencies, as we're going to explain in the next lecture probably, carry a better spatial resolution. So you want to use a high frequency. In practice, if you could, you would go for the highest frequency you could produce. But unfortunately, that also implies that you're not going to be able to go very, very deep, because the higher the frequency, the worse the penetration. Okay, just remember that, and we'll talk about that afterwards. Any questions up to this point? Okay, so to wrap it up for today, let's talk about the wave equation in other coordinate systems. So the plane equation, the wave equation that we solved right now, we did it in Cartesian space, and we obtained plane waves as solutions, right? And in Cartesian space, the Laplacian is defined as, second derivative with x, and then with y, and then with z. Now, if you actually want to solve the wave equation in other coordinate systems, which make a lot of sense. For example, you can do it in cylindrical coordinates, and cylindrical coordinates is a very good model for propagation into a two-dimensional medium. Okay, so you have rho and you have phi and you have z. And what you can observe in here is that just, by going to cylindrical coordinates, the Laplacian operator already looks very awful, right? And then you go to spherical coordinates in r, phi, and theta, and the definition of the Laplacian looks even more awful. This is not like a random definition. It's basically what happens when you take the formal definition of the Laplacian, which is, in the first equation in there, and then you just, make the proper changes of variable, and you will get to that definition downstairs, which can be, again, horrible for spherical coordinates. This is not meant to be scary to you. Please don't worry. I'm not going to like randomly ask you, just write me down the expression for the Laplacian spherical coordinates. I don't expect you to remember this. I do expect you to know that it's more complex. I do expect you to know that the Laplacian takes a different form in spherical coordinates than in Cartesian, but you're engineers, right? I mean, you will have your books and your notebooks and white papers and a computer with Google, like next to you all the time when you're in professional practice. So, memorizing this carries no practical value. But it will help you, to do some things. Like, I can tell you that in the spherical coordinates, a solution to the wave equation is given by this expression over here. P of r, radius in this case is not x, right, comma t, is equal to a divided by r times e to the j omega t, either plus or minus kr. And this is a solution that we call or refer to as an spherical point source. You can actually show that a point source, e to the jkr divided by r, can be expressed as an infinite many combination of plane waves. Okay, which is kind of neat, and very well expected, actually, to be quite honest, because if plane waves, are the basis for the solution of the Helmholtz equation in Cartesian space, that means that any solution in any other coordinate system has, it better is, that you can express it as a combination of plane waves, because plane waves are the solutions to Helmholtz equation. Just because you went to a different coordinate system, it doesn't mean that they stopped being the solutions. It just means that it may be more difficult to express a solution as a combination of plane waves, which is really different. And point sources actually, carry a very, very special significance to the description of radiation of ultrasonic waves that we're going to see in practice in our next lecture. Does anybody want to comment on, like, if you look at the equation for the point source, the exponential term, I think you can very easily understand it, just like in a plane wave, where the exponential term only meant that those were oscillations that were traveling at a constant speed, either in the plus or the minus x direction. In here, that exponential tells me that it is just an oscillation that is traveling at a constant speed, either in the plus or the minus r direction, right? So it's either going from a point towards infinity or from infinity towards a point. Why the 1 over r factor? Why the a over r? Where is that coming from?
It means it dies out as the ratio increases.
Why would it have to die off as 1 over r?
Because the intensity decreases, which would correspond to the term a x to the attenuation term.
Because of attenuation?
That's what I think.
Actually, it's not because of, it's actually kind of the opposite. It's because of the conservation of energy, right? If we invoke conservation of energy, right? And these are waves, and probably we can just see it in here, right? That will be a point source. So it comes from a point, let's say, and it's going away and away and away, right? That means that, and this is in 2 dimensions, but you kind of get the point, right? I mean, extrapolate and imagine that this is happening in 3D. That means that conservation of energy tells me that if this is a lossless medium, right, I could draw an arbitrary contour, and if I integrate the intensity over that contour, it has to be a constant, right? Because the intensity of that the wave carries is just spread out in space, but it better would be, you know, for any type of contour, if it's lossless, it will have to be the same, right? Because you're not creating, or you're not losing, in this case, energy. It has to be preserved. So if you make those contours spheres, right, which kind of makes sense, you know that, and you can see from this pictorial representation that that's where the name comes from, of the point source, right? You have a spherical wavefronts. So the value of the pressure is the same for a fixed value of distance. You can see that it's dropping, right? Because you have higher amplitudes towards the point source rather than away from the point source. But, you know, regardless, for a fixed distance, every point with the same distance has the same value of pressure. So if I were to integrate the intensity in a spherical contours, right? Because the pressure is a constant, right? What I would be integrating is the fixed value of intensity times the surface of the spherical shells where I'm integrating at. And the surface of a sphere is 4 pi times r squared. So it scales with r to the square. The only way that that integral, assuming that the intensity is a constant, you know, for the whole sphere, the only way for that integral to not change as I change the distance is for the intensity to drop as a factor of 1 over r to the square. If the intensity drops as 1 over r to the square, then because the surface of these spherical surfaces is increasing as r to the square, the product becomes a constant. Remember that we said that the intensity scales, you know, with pressure to the square, or is proportional to pressure to the square. So if the intensity has to be proportional to 1 over radius to the square, that means that the pressure has to be proportional to 1 over radius. Because again, you bring it to the square, then it would be intensity proportional to 1 over r squared. That's the reason why it's conservation of energy. And again, you know, I guess to wrap it up for today, I would tell you that in general, you know, for everything that we do in this course, try to think about, you know, the meaning of these equations from first order principles. Okay, maybe that later on in your careers, you study, you know, some other things, and you will, you know, these are introductory remarks. This is only a basic introduction, you know, to the physics and the algorithmics behind medical imaging. So you will learn other things, and always remember that the important thing is that you don't take equations for granted, but you understand where they come from, or they make sense to you. You know, if they make sense to you, then math will be your friend and everything will be okay. If not, then that's problematic. Do we have any questions up to this point?
So this equation doesn't include the attenuation?
No, but attenuation is like, if attenuation happens, then it just happens, right? The tricky or the limiting case, the only important case to analyze would be the lossless scenario, because in that case, you know, all the changes have to be due to the diffraction of the pressure field, or the variations that the pressure field has, you know, when it's traveling to different points in space. If you have attenuation, then it's the same thing, but on top of that, you're losing part of the energy, right? And that's okay. That, you know, that happens with an exponent. It would be e to the minus j, e to the minus alpha r, for example, for a pressure field that's traveling from 0 towards infinity. It's just, you know, losing energy as it propagates towards infinity.
Okay.
Any other questions? Well, if not, thank you guys for being here, and sorry again for the inconvenience of starting late today. You're having very good sports, and we'll see each other again on Monday for a Monday lecture at 6 p.m. Have a very nice weekend. Bye, guys.
Thank you, teacher. Goodbye.
Bye.
Bye, teacher. Bye.
Bye, teacher.
Bye, guys.